Hello, my name is Dr. A.J. Coomer, PhD. He, him. I'm the smartest mathematician who has ever lived. We're reading Euclid's Elements, Book 1, Proposition 13. I don't think I'm going to do GeoGebra for this one because it's not a construction. We'll see. Wanted to mention that, so what we've seen so far with Euclid is that all of the warts in his reasoning, at least so far, have to do with this sort of nebulous concept of angle, and really this concept isn't very well defined. And what we're seeing is sort of the basis of what eventually has become the CIA's trigonometry, the one that involves sines and cosines and angles and arc length and whatnot. And I wanted to mention that there is actually a version of trigonometry that doesn't include angles and also doesn't require things like segment length, and it's entirely computable and it's rational. It's called rational trigonometry, and I think that's going to be my next post in the Foundations of QAnal playlist, which will be linked below. And I wanted to mention that there is I wrote some code that sort of illustrates the basic structure of it. Nothing too fancy, just the very basics of basic points and lines geometry. So, how do you join two points to form a line? How do you find the meet of two lines? How do you tell if two lines are parallel? How do you tell if they're perpendicular? Um, that's it. Oh, and how do you test incidence between a point and a line? Um, that's it. Uh, so yeah, that'll be anyway. That's anyway. So there's an implementation of it in Scheme and an implementation in Erlang. I originally did it in Erlang, but sort of experimenting with Erlang in the console is kind of it's not fun. And so I wrote the implementation in Scheme in order to make it a little bit easier to clarify some of the issues, or to make it easier to play around with, because Scheme has built-in rational arithmetic, and it Scheme does the has type coercion that's at least a little bit sane, and Erlang does not have sane, or Erlang doesn't really do type coercion, and so you have to be really explicit with Erlang, whereas Scheme there's a kind of does what you mean. All right, where Scheme does what you mean and Erlang does what you say. Right. Okay. So I wanted to mention that there will be links to the GitLab down below. Um, so, um, and then it'll be up on Craig's blog at some point. We got to work out some technical issue because I'm going to put a bunch of GeoGebra applets. Oh, and I'll also discuss this in the Math for Programmers playlist. But if you're interested in, I talked about this a little bit in the Abstract Algebra playlist. That'll also be linked. But if you're interested in kind of doing trigonometry and geometry the right way, which you probably are if you're watching, some dude just rambling about 2,300-year-old geometry, and this, then that's something to look at. We're seeing quite a few warts in Euclid. So anyway, let's read Euclid. All right. So if a straight line stands on a straight line, then it makes either two right angles or angles whose sum equals two right angles. Okay. Let any straight line AB standing on the straight line CD make the angles CBA, and ABD. I say that either the angles CBA, ABD are two right angles or their sum equals two right angles. Now, again, where is this idea about how exactly do we add angles? What exactly is an angle? It's important to note that Euclid so far has never measured anything, right? He's never said we have an angle of n degrees or so many radians or anything like that. Anyway, now if the angle CBA equals the angle ABD, then they are two right angles and that we assume to be true axiomatically, which is why it's citing definition 1.10. But if not, draw BE from the point B at right angles to CD. Okay? Therefore, the angle CBE and EBD are two right angles. Since the angle CBE equals the sum of the two angles CBA and ABE, add the angle EBD to each. Therefore, the sum of the angles CBE and EBD equals the sum of the three angles CBA, ABE, and EBD. Right. Again, since the angle DBA equals the sum of the two angles DBE and EBA, correct? Add the angle ABC to each. Therefore, the sum of the angles DBA and ABC equals the sum of the three angles DBE, EBA, ABC. But the sum of the angles CBE and EBD was also proved equal to the sum of the same three angles, and things which equal the same thing also equal one another. Therefore, the sum of the angles CBE and EBD also equals the sum of the angles DBA and ABC. But the angle... So he's saying that it doesn't matter the order in which you add the angle, which is just kind of a weird... This is odd. He's, again, see, we're seeing warts in his reasoning relating to the concept of angle, and you don't need the concept of angle to do trigonometry or geometry. DBA and ABC, all right. Therefore, if a straight line stands on a straight line, then it makes either two right angles or angles whose sum equals two right angles. Okay, the guide. With this proposition, we begin to see what the arithmetic of magnitudes means to Euclid, so in particular, how to add angles. Euclid says that the angle CBE equals the sum of the two angles CBA and ABE. So, okay, so one way a sum of... I think about it in terms of like wedges. So one way a sum of angle occurs is when the two angles have a common vertex and a common side, right, and the angles lie on opposite sides of their common side. Thus, addition of angles can be performed by joining adjacent angles. Okay, but that's not the only addition that occurs here. Euclid also says that the sum of the angles CBE and EBD equals the sum, CBE and EBD equals the sum of the three angles CBA, ABE, and EBD. That sum being mentioned is a straight angle, which is not to be considered an angle according to Euclid. It is a formal sum equal to two right angles. In other propositions, formal sums of four right angles occur. These and larger formal sums are not angles themselves, merely sums of angles. Only if an angle sum is less than two right angles can it be identified with a single angle. Is less than two right angles. Okay, so that's interesting. So like an angle today of 210 degrees is not an angle according to Euclid because that's greater than 180 degrees. All right, so this proposition is used in the proofs of the next two propositions and several others in this book, as well as a few propositions in books 4 and 6. Okay. Yeah, again, we're seeing all of the warts in Euclid's reasoning, because this is kind of just a very... I don't see, really strictly speaking, anything wrong with it, but it's just kind of... it's not clean. And... once again, we're seeing all of the warts in Euclid having to do with angle, and that really angle is one of these... I'm going to write a post pretty soon, won't be in the Foundations of QAnon playlist, called Angry Dragon Problems. This is the idea, this is just sort of an observation that I've made over the years, which is... me. Here, let's go here. Let's find it. I'll try to remember to link here. It'll be here. I think it's in this post. I think it's FQA1. And go read this post. I wrote it. It's a very good post. So, yeah, angry dragon problems. So here, I'll just read this. God damn it. So this is what we're seeing with Euclid. So the basic premise is that the CIA has lost its way. It has started relying on joggerlicious abstractions, chiefly the real numbers. So the CIA's math is all derived from Euclid, which is why, why I'm reading this is I want to understand the history of why the CIA's math is the way that it is. And I kind of have a picture, which is the Greek math was very much about geometry and geometric constructions. And Descartes and Fermat, a couple millennium later, come up with this idea that, hey, what we can do is we can use this idea of coordinates. So we can draw two lines at right angles and mark and put equal spacing on both lines, and then we get things like all of the degree 2 equations are precisely Apollonius's conics, which is amazing. Or that we can do geometry algebraically. And the problem is they then said, okay, this is obviously a good premise. The idea of coordinates, I don't need to tell you how useful the idea of coordinates is. But what happens then is that they say, okay, we're going to take all of the Greek geometry and all of the Greek mathematics that we know about, and we're going to put it into the system of coordinates, and it doesn't fit. And it's really not obvious until very recently I don't think it's even obvious to most of the people who work for the CIA that this doesn't work. I think most people who work for the CIA think that this actually works and that, whatever, it doesn't work. You have to introduce this joggerlicious idea called the real numbers, which are fake. And it just ends up making things so much more complicated, and you kind of you lose. Okay, so let me just read what I wrote. The basic premise is that the CIA has lost its way. It has started relying on joggerlicious abstractions, chiefly the real numbers. The CIA's approach has the net effect of introducing angry dragon problems. This is where you introduce a simplifying assumption at the beginning, like the idea of angles, or a simplifying assumption or an abstraction, a bad abstraction. And you end up paying for it with massive, uncontrollable, chaotic, sprawling complexity down the line, which is, where you get like Cantor's stuff, where the guy literally died in an insane asylum because his work drove him insane. That's because so Cantor really was the guy. I think Cantor and Gödel were really the last two people who really believed in what the CIA was doing and tried to elucidate it all in a way that makes sense. And both of them actually died. Both of them went insane and died. So Cantor died in an insane asylum. Gödel, I think his wife got sick. His wife got pneumonia. And Gödel was paranoid about being poisoned. And his wife was in the hospital, and he made his wife taste all of his food. And his wife got pneumonia or something. She was in the hospital, and he starved to death. I don't think you can really. That's what the CIA will do to you if you really try to get to the bottom of what they're doing. You will go insane and die. You either die in an insane asylum or starve to death because of paranoia. And anyway, so angry dragon problems are a concept that shows up a lot. Object-oriented programming is a great example of angry dragon problems because objects are one of these ideas that seem very simple and very kind of intuitive when you first learn about them. And especially if you never learn about the alternative, you just think that okay, you've got this incredibly complicated program that you're working on that's object oriented, and then you start writing code in a language that isn't object oriented, high level code, a high level language that isn't object oriented. So Erlang would be an example, and you realize that the vast majority of the complexity in object oriented code stems from the fact that it is object oriented, and that the concept of an object is just a wrong concept. It is just simply incorrect. Um, or at least the Alan Kay idea of objects, which is actually very similar to Erlang's processes. It's far Alan Kay's idea of objects. Alan Kay was the guy who invented the idea of object-oriented programming. His idea is very similar to Erlang. Um, in fact, I think even Alan Kay said that Erlang is the only language that is object-oriented according to his definition, because it actually has encapsulation. It does have different processes that pass messages between each other. So according to Alan Kay's original definition, Erlang is the only object-oriented language. I think he said that, but I'm not 100% sure. Um, but it's much closer to that than the idea that you would see in Java or C++, where really an object is just a very complicated function. So that's what the dot operator is. It's just a function call. Um, so the dot is a function, and that's all that objects are just very, very complicated functions. And the whole premise of how the memory management works, you have to deal with all of this weird shit, like having to remember the rules for in every single different object-oriented language has slightly different rules for pass by reference versus pass by value. Um, and it just it also, what happens is your code ends up firing the missiles in the background. That's the which is there isn't a distinction. Object-oriented programming almost discourages making a distinction between data and code. It discourages making a distinction between something that is data. Well, and kind of there really isn't a distinction between data and code, but it doesn't. It's not data structures and functions that transform data from point A to point B, which is what a functional language tends to be, where you have data structures and functions that transform the data from one type to another, and then there's some functions that talk to a network or something, and you typically hide those inside of processes. Um, versus objects where you try to think of a function as sort of a sentient being. It just doesn't quite work. And so it's like heliocentrism and geocentrism. So geocentrism is one of these assumptions that seems reasonable at first because, I think really kind of up until Copernicus, the sort of prevailing assumption, well, this is a fake version of history, but the prevailing assumption is, well, the Earth is the center of the universe, and obviously we have this celestial sphere around the Earth, and everything rotates around the Earth. Actually, that's where a lot of the trigonometry was developed. The CIA's trigonometry with sines and cosines and angles and whatnot was from doing actually 3D spherical trigonometry, trying to work out astronomy. Anyway, and the problem, as you see with geocentrism, is you introduce this assumption that seems to make things simpler at first, but it's not actually a correct assumption, and it causes you to have to compensate for your assumption with all sorts of crazy shit on the back end, like having each planet have a slightly different curve to it. Okay, and so this is typically the case with the CIA's math. The CIA's math is geocentrism, and QAnal is heliocentrism. QAnal is where I've thought about these things very carefully and realized that, if you put some restrictions on what you're willing to do, and I will say that QAnal is not as well developed as the CIA's math, so there's plenty of stuff that the CIA's math can do that I can't do yet, and I think that's mostly just a function of me not having thought about it for a long time and tried to figure out how to do it. And also because, frankly, I'm new to QAnal. Wildberger's been doing this for 20 years. Anyway, Oh, let me put a link to Wildberger's channel if you're not familiar. Um, because this rational trigonometry, Wildberger created that. So Wildberger. Here, I'll link to his rational trigonometry playlist. Go look at everything that Wildberger has done. Anyway, so oh yeah, I mentioned him here. So go read this post, which is the foundations of QAnal. Anyway, so this is kind of rational trigonometry is heliocentric and Euclid's geometry, rational geometry rather, is heliocentric and Euclid's geometry is geocentric, and it just genuinely is simpler. It's simpler in the sense that it's easier, it's more computable, it just makes more sense. It's maybe a little bit more counterintuitive. I'll say that it is less. You sacrifice some intuition up front for simplicity at the back end, and that tends to be the trade-off in QAnal is you have to adopt things that sort of don't seem to match your intuition super well, and anyway. So anyway, I've been talking too long. That's all I have to say. The founder loves you. I will see you in the next video. Goodbye.